days, holidays, days off, sometimes it's hard to maintain the thread of what we're doing. So let me just remind you. Actually, the first thing we can notice is that the person who cleaned the blackboard was obviously short because they couldn't reach this part. They can only clean from here down. First lesson of the day. Okay, if you remember, as the semester was going on, we realized that before we could do control, we had to learn how to do modeling, particularly unsteady state modeling. And unsteady state modeling involved equations with a term that you aren't used to, DDT, which in all your other classes you threw away. And this required us to be able to do the models and solve them. We started out solving models using the straightforward methods of ordinary differential equations, where we found that the models we wrote down, not all chemical electrical models, but the simplest models we could write down were first order linear differential equations, ordinary differential equations in time. Obviously, there were no space derivatives in those equations. If they were, they would have been partial differential equations like you would have in a unsteady transport problem. We avoided those so far. They exist, we just didn't touch them. So we started solving ODEs using the methods of, particularly linear first order ODEs, using the methods of differential equations from your ODE class. And then we saw that some models were nonlinear, not just linear. It was pretty easy to come across nonlinear models. So what we did is we said, well, we have tools for linear equations. Let's see if we don't have tools, very good tools for nonlinear equations. But as long as things don't go very far from the linear state, maybe we could just linearize about the state, about the previous situation, say the steady state value, and then we could solve linearized equations, again using the same formula. That worked very well. The only issue was there was a lot of writing, and with a lot of writing often means a lot of mistakes. So we said, is there another method of doing it? And so we decided to look at methods of Laplace transforms, which forms another method for solving ordinary differential equations, and not just first order, of any order. But it's particularly useful for linear equations. But they couldn't be of any order. And what we did is we noted that in order, so we take a Laplace transform, and the wonderful thing about Laplace transforms is all the derivatives and integrals disappear. So if we have a differential equation and we take the Laplace transform, instead of just getting the derivative of the function, we get s times s, which is the Laplace transform variable, times the Laplace transform of the function. So a derivative becomes s times something. An integral becomes something divided by s. So an integral differential equation just turns into an algebraic equation. And you could imagine if I had a partial differential equation, if I were doing a problem from an unsteady problem from transport, then the partial differential equation with the ddt and all the derivatives with respect to position would become an ordinary differential equation, or at least the ddt would disappear and I would only have the derivatives with respect to position. Once I then solve the problem for the Laplace transform of the thing I'm interested in, then I, of course, have to invert it because I don't really care that much about the answer in the Laplace domain. So we noted we have this table, which is sort of the easy way of doing the inversions, where in one column we have the function of time, and in the other column we have the corresponding functions of s. So if we find something in the right column, we just look across to the left column, and that allows us to do the inversion. And of course, there are tables that are longer than this. This is 1 page. You can find tables that are 3 or 4 pages. What we noted, however, is no one is going to list all possible functions. First of all, there are an infinite number of them. And secondly, if you can write one function as the product of a few of these, or the sum, more like the sum of a few of these. If you could write one function as the sum of a bunch of these, no one's going to write that sum out because there are an infinite number of sums. So you have to learn we have to learn how to take a function that looks ugly and break it into a sum of the simplest forms of those terms, and then look for each of those terms in the table. So that's where we were, and we also noted something where the initial value theorem, the final value theorem, where we can get some information directly from a Laplace transform without inverting. But if we want the full time dependence, we have to do the inversion. So we looked at the various cases. So we were looking at inverting the Laplace transform. Well, we were looking at partial fractions. Which is the way of breaking up a big function into a sum of easier functions that we can then try to invert. And for case one, so here we have a function which was n tilde of s over d tilde of s, which we can call m tilde of s. So we have function m tilde of s, and we're assuming that it's the ratio of two polynomials, because that's what we typically get in this class, in these models. So I've got n tilde over d tilde, where n stands for the numerator and d for the denominator. And in case one, so here, n tilde of s and d tilde of s, polynomials. In case one, d tilde of s has distinct roots. In other words, I can write d tilde of s as s minus s1, s minus s2, dot dot dot, s minus sn, where s1, not s2, dot dot dot, sn are all different. And we saw, that's what I mean by distinct roots. And in that case, we saw that m tilde of s could be written as a sum of mj over s minus sj, j equals 1 to n, plus possibly some remainder, I can call this cj, where cj was equal to mj of sj. And what's mj? Where mj was of s. Well, why don't I stick with C1? Where m1 of s is equal to n1 tilde of s, since this is a function of s and the tilde is over it, divided by all the products s minus s2, dot dot dot, s minus sn, where I leave out this product. I leave out this guy. That's m1. And therefore, when I evaluate this at s1, since all the sj's are different, there are no zeros in the denominator. And notice, I'm assuming that there are no common factors. And if n1 is a polynomial, I just evaluate the polynomial at s1. And so what you do is you write it as c1 over s minus s1 plus something else. And then the something else you break up in the same way as c2 over s minus s2, etc. And we noted that if f tilde of s is 1 over s minus sj, then this corresponds to f of t is equal to e to the sjt. So we said that was the correspondence. Now, one thing to note is I can also note, which I didn't bother noting last time, but let's just note that C1 can be written as n tilde of s1 divided by, so this is m tilde of s1. Instead of writing the denominator this way, I could write it as d tilde ds at s1. So that's another way of writing the same thing. And let's just verify that. Well, for a polynomial, it's straightforward. If this is d tilde, then let's look at d tilde of s1. So this is equal to n1 tilde of s1 And what's the derivative? Well, I've got the product rule. It's the derivative of this factor times all the rest, plus the derivative of this factor times all the rest, etc. So the first term is s minus s2, s minus s3, dot 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 s minus sn, plus s minus s1 times s minus s3, dot 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 s minus sn, plus dot dot dot, plus s minus s1, dot 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 s minus sn minus 1. So I took the derivative of the first factor, that one left, I was left the rest. Derivative with respect of the second factor times everything else, the s minus s2 went away, all the way until I get rid of the last factor. When I evaluate this at s1, notice that all except the first term have an s minus s1 in them, so these all disappear. And I'm just left with this, which is exactly the right answer. Now, this is useful if I had something that wasn't a polynomial. For example, what if d tilde of s was equal to sine of s? For an example. Now, this of course violates this being polynomial, but it may come up. So it's hard to write the sine of s as a product like this because it's not a polynomial. But this formula still works because then let's notice what the zeros of s are. What are the zeros of the sine? When is the sine 0? At 0, pi. So notice that s, sine of s is 0 when s is equal to n pi. N equals 0, plus or minus 1, plus or minus 2, etc. So if I wanted to, if I want to calculate C1, this would be N1 tilde of S divided by, and let's say at S is equal to 0, so divided by the derivative, d sine S ds at S equals 0. And that I can calculate very easily. N1 tilde of S, whatever that is, of 0, divided by the cosine of 0, where the cosine of 0 is 1. So this just becomes N1 tilde of 0. So it's useful to have this formula, because sometimes even when something's a polynomial, you don't want to go you may not want to bother factoring it. In this form, just take the derivative. It's an easy way of doing the calculation, as long as you know that there are no multiple roots. Any questions on that? So that was case 1. This is all review so far except for this. In case 2, we had d tilde of s was equal to s minus s1 raised to a power, did I call it n or n plus 1? N plus 1. And I think I called it alpha. The n plus 1 times other stuff. Times other stuff. Maybe I called other stuff, gave it a symbol. No, I think I just did it as n tilde of s. Yeah, times other stuff. So in which case, m tilde of s was equal to m1 tilde of s divided by s minus alpha to the n plus 1. And what we showed last time was, therefore, we could rewrite this, m tilde of s was equal to, and let's get the notation right, n plus 1. This is a review from last time. You should have this in your notes. So we could write this as C1 over s minus alpha plus c2 over s minus alpha squared plus dot 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 plus cn plus 1 over s minus alpha to the n plus 1, where we noted that if f tilde of s is 1 over s minus alpha to the n plus 1, then f of t corresponds to, and that was from our sheet, then f of t was equal to, let's see, I think I did it, well, it doesn't matter. If this is, let's say, to the n, doesn't matter. That's what I have in my notes. That's equal to t to the n minus 1 over n minus 1 factorial e to the alpha t, right? Yes. And I gave you formulas for the c's. And I gave you a formula, and let's just copy that down since I don't feel like rederiving it. I had c sub n plus 1 minus j was equal to the jth derivative of n1 at alpha divided by j factorial. So that's all review, and we derived that last time. And how did we finish the hour last time? We finished the hour last time by preparing for the next case, for case 3. And the one way we prepared for it is we noted that we can the only way to define e to a complex exponent, or e to an imaginary exponent, say e to the I x, was to define it as cosine x plus I sine x. And from that you can easily find that the cosine of x is equal to e to the ix plus e to the minus ix over 2. And sine x is e to the ix minus e to the minus ix over 2I. But that was the only, that this implies this. There's one other thing we need to do in order to prepare for case 3. And that's just to get a little workout with complex numbers. So if you recall, let's let z be a complex number as x plus iy, where again I squared is equal to minus 1. So I think we're all familiar with the basics of complex numbers. So the first thing is I claim that at z bar is defined as the complex conjugate is x minus I. So when I put a bar on top, I turn I into minus I. And if I put 2 bars on top, I turn the minus I back into a plus I. So the first thing let's notice is that z1 plus z2 bar is z1 bar plus z2 bar. Let's just prove that. x1 plus iy1 plus x2 plus iy2 bar is equal to x1 minus iy1 plus x2 minus iy2. Well, that's just equal to x1 plus iy1 bar plus x2 plus iy2 bar. So that's just the proof of this. Next statement. z1 z2 bar is equal to z1 bar z2 bar. So let's prove that. So here I have x1 plus iy1 times x2 plus iy2. Let's figure out what that is. That's z1, z2. That's equal to x1, x2 plus I squared is minus 1, y1, y2, plus I times x1, y2 plus x2, y1. So I just multiplied out the 4 terms. And so therefore, let's look at what z1, z2 bar is. z1, z2 bar is x1, x2 minus y1, y2 minus I, x1, y2 plus x2, y. You don't have to worry about writing all this down. You're going to have the photo of this. I'm writing quickly. The algebra is easy, So it's better for you to try to understand what I'm doing rather than copying furiously. You'll have a picture of this, it's no problem. Just try to follow what we're doing. Okay, so this is Z1, Z2 bar. Now let's multiply Z1 bar times Z2 bar and show it's the same thing. That's x1 minus iy1 times x2 minus iy2. Well, that's equal to x1, x2 minus the squared, minus 1 squared is plus 1, I squared is minus 1, times y1, y2. And now I have minus I times x1, y2 plus x2, y1. Well, lo and behold, this is exactly the same as this. So that's proof. So what do we say when we take the complex conjugate of a sum? It's the sum of the complex conjugates. When we take the complex conjugate of a product, it's the product of the complex conjugates. So what we can find from here, and this one I'll let you prove for homework, using these, is if I have a polynomial, P of Z bar is a polynomial, then this is equal to P of Z bar. If I take the complex conjugate of a polynomial of Z, and why is that? Because how do I get a polynomial? I take products and sums, and I know products and sums work. Okay, so that takes us, are there any questions on that before we go to case 3 now? Okay, case 3. Case 3 is where m tilde of s is equal to m1, what notation do I want to use here? Actually, so let's make it n tilde of s over d tilde of s is equal to m, I want to give this some name, m sub a, tilde of s, divided by s minus alpha squared plus omega squared, where alpha and omega are real. And I claim that I can write this as m1 tilde of s divided by s minus alpha plus I omega plus m2 tilde of s over s plus alpha, minus alpha minus I omega. And let's just make sure I got that right. Yes. Okay, so first let's notice that I claim that these two things in the denominator are the factors of this. So let's just notice, so let's just notice that what the factors are. So let's notice that s minus alpha squared plus omega squared is equal to s minus alpha plus minus I omega times s minus alpha plus I omega. Well, why is that? Well, let's just multiply this out. Let's consider this one guy. This is the real part. So if I multiply it out, again, you don't have to write everything. You're going to get a picture of this. So it's this times this, that's s minus alpha squared, plus this times this, that's minus 1 squared, and I squared, which is minus 1 times minus 1 is plus 1, omega squared, plus omega squared. And then I have s minus alpha minus I omega, and then I'm adding s minus alpha plus I omega. They cancel. So these are just the two factors down here. Any questions of that? So it's just like what we did before. We factor the denominator, and then we write it as something over the first factor plus something over the second factor. The difference is between this and case 1 is that now I have complex numbers down here, not real numbers. And again, I am assuming that alpha plus or minus I omega are simple roots. Simple means there aren't two of them. There's only one of them. The other thing is, if I have a polynomial where all the coefficients are real, remember like in a quadratic, I mentioned it last time, if you have a quadratic equation or any higher order polynomial where the coefficients of the polynomial are real because they come from a physical process, then you can have complex roots, but they always come in pairs, the complex conjugates. So like in a quadratic, it's minus b plus or minus the square root. If the inside of the square root discriminant is negative, you get I times something. But I don't just get one of them, I get the plus or the minus. And it's easy to show that because if you didn't get the plus or the minus, when you multiply things out, you'd have a coefficient of the polynomial that was complex, at least one coefficient. If all the coefficients of the polynomial are real, then the complex roots have to come in pairs, complex conjugate pairs. Okay, so first I'd like to figure something out about M1 and M2 tilde. I claim that I'm going to multiply through by, let's call this thing Z, and this thing Z bar, just to make the notation a little, so I don't have to write as much. So I'm going to multiply through by S minus Z times S minus Z bar. And I'm going to multiply star by that, where this is star. So that tells me that MA tilde of S is equal to, it's equal to M1 tilde of S. Well, I'm multiplying by S minus Z, they cancel, S minus Z bar. And the next term, M2 tilde of S, is multiplied by S minus Z bar, that cancels, and I'm left with an S minus Z. I'll just multiply through. Now what I'd like to do is I'd like to take MA tilde of Z and MA tilde of Z bar. By the way, I also want you to show that P1 of Z, P2 of Z tilde is P1 tilde of Z over P2 tilde of Z. So I also want you to show that if I take Z1 over Z2, that follows from knowing Z1 over Z2 bar is Z1 bar over Z2 bar. Okay, so, well, if I evaluate this thing at Z, this is 0, and I'm just left with M1 bar of Z times Z minus Z bar. Well, let's see what Z minus Z bar is. Note, Z minus Z bar, actually I can do it right from here. Z minus Z bar, well the x's cancel, and I get IY minus a minus IY is 2IY. And MA tilde of Z bar, well at Z bar this is 0, so I'm left with M2 tilde of Z bar times Z bar minus Z. Well, Z bar minus Z is the other way around. Z bar minus Z, the x's cancel, but I've got minus IY minus another IY. I get minus I times 2I. And I can notice that this is MA of Z and this is MA of Z bar. Well, since the ratio of polynomials, the complex conjugate of that, and actually these should be bars and not tildes, bar. The ratio of complex conjugate, the bar of the ratio is equal to the ratio of the bars. This is just the complex conjugate of this. So I'm going to take the complex conjugate of this guy, MA tilde bar of Z. And that's the complex conjugate of this, which is M1 tilde of z quantity bar times the complex conjugate of this, which is minus I to y. Because the complex conjugate of the product is the product of the complex conjugates. The complex conjugate of the product is the product of the complex conjugates. Now this thing, since these are complex conjugates of each other, the complex conjugate of this equals that. So these two are equal. These are equal. Well, if they're equal, these two guys are the same. So that tells me that n1 bar tilde of z is n2. So therefore, n1 tilde bar of z is equal to n2 tilde of z bar. But we know, so this follows, but we know because of this, that this is equal to, so this implies this, that this is equal to n2 tilde bar of z. So what have we shown? That n1 tilde bar of z, tilde of z, n1 tilde bar of z is equal to n2 tilde bar of z. So therefore, n1 and n2 are the same. They're the same function. Okay, all that is, this is the result. If you don't like the math, you can just believe it, but I wanted to prove it for you. I'm not going to test you on the proof. So the important thing is n1 and n2 are the same function. Okay, any questions on that so far? All right, so now let's, now this is not, shouldn't be of S, this should be of alpha plus I omega. And this should be of alpha minus I omega. It's evaluated somewhere, just as this guy was evaluated somewhere. It was evaluated somewhere. It wasn't just sitting in the blue. C1 had to be n1 tilde evaluated as S1. So these are evaluated at these places. So what we now know is n2 is the same function of S1 as n1. But this is evaluated at alpha minus I omega, and this is evaluated at alpha plus I omega. These are complex conjugates of each other. So so we can note that m2 tilde of alpha minus I omega is just some complex number. It's a complex number. Let me call it a plus ib. It's a complex number. Well, this guy is the same function, but at the complex conjugate of its argument. And we said that the function at its complex conjugate is just the complex conjugate of the function of z. So in other words, m1 tilde of alpha plus I omega, by virtue of this, is just equal to a minus ib, just the complex conjugate of that. Okay, so now we can start doing something. So let's notice something. All right, so now we have okay, so this thing now is equal to, and let's invert. So now let's invert n tilde of s over d tilde of s. Inverted to some function of t. So I have a coefficient here, a plus ib. And we know that 1 over s minus something, I wrote that down, 1 over s minus something just gives me, when I invert it, e to that something t. So now I have, this is times e to the alpha minus I omega times t. Because I just have something, a number over s minus something. And 1 over s minus something inverts to e to the that something t. Plus A minus IB this guy, and did I do it right? Yeah. And this is 1 over s minus something, so I need e to that something t. E to the alpha plus I omega t. Is it clear what I just did? Half the class is missing, and they're going to miss this, and they're not going to understand it. Please make sure to sign the attendance sheet. When I see someone's missed 3 classes, I have to tell the registrar that they don't come to class. Okay, so let's rewrite this. So I have a times, and notice that I have e to the alpha t on everything. So let's pull the e to the alpha t out. And here I have a times e to the I omega t plus e to the minus I omega t. And now I have plus b times, well, what do I have? B. I have b times I. Actually, let's put a minus b. Minus b times I. Minus ib times e to the I omega t. And minus b times I is going to give me another minus sign here. Minus e to the minus I omega t. Is that clear? What I did was I factored that out, multiplied it out. Well, notice I can multiply and divide by 2 here. And I can multiply and divide by 2i here. And if I do that, I can note that this is cosine omega t. And this thing is sine omega t. So I have e to the alpha t times, well, I've got a 2, because I can factor out a 2. And here I have an a cosine omega t. And here I have an I times an I is a minus 1, times another minus 1 is a plus 1. So I have plus b sine omega t. And that tells me that n tilde of s over d tilde of s, Laplace transform inverse, is equal to this. Now, of course, I think your book just tells you the answer. I don't think they bother to write it. But let's notice what this is. Let's compare this to the others. Remember this thing, e to the st, if s is negative, so if s is positive, it looks like this, and if s is negative, it looks like this. No problem. Just exponentials. This guy, for n greater than 1, when n is greater than 1, notice that if alpha is positive, it just grows. And so if alpha is positive, it just grows as e to the alpha t. And it starts when t is 0, it starts at 0, and then it grows exponentially, alpha greater than 0. If alpha is less than 0, let me just finish this. If alpha is less than 0, the exponential wins, but at small times, t grows. So if alpha is less than 0, it looks like this, because at small times, this is pretty close to 1, and I just see t to the n starts growing. But once t gets of the order of 1 over alpha, this takes over and it dies. So notice no oscillations. It goes up and down. Yes, question?
If we lose an I in that box solution, should be I b times.
I'm sorry, where are you?
In the box solution,
Did I?
shouldn't that be an I and b?
It's b times I squared. I squared is minus 1 times minus 1 is plus 1. Isn't that nice? All the i's disappeared. So the i's don't have it. Okay, and let's see what this guy looks like. this guy has an oscillation. And alpha, if alpha is greater than 0, then what happens is it's a growing oscillation. It's a growing oscillation where I have an envelope. Actually, I should draw the envelope first. It would be easier to draw it. Let's draw it a little nicer. So that's alpha greater than 0, and alpha less than 0. I have an envelope that looks something like this. So this is very different. Here, it oscillates and grows. Here it oscillates and decays. And if alpha happens to be equal to 0, it just oscillates. So it's nice every now and then to plot something, not just to look at the formula. And let's think what's going on here. Remember, we can get these roots of a polynomial with real coefficients. Physical problems give me real coefficients. I could have real coefficients giving me complex roots. So I could have non-oscillatory inputs, simple inputs, and the output starts to oscillate. And now, if this is the pressure, if your function is the pressure, this is really bad. When the pressure starts getting really high, kaboom. This isn't so terrible, but it does oscillate. And this one just oscillates forever. So notice I have all these possibilities. And that gives me the question of stability. And we can classify systems. Now, by the way, notice what we've done here is once we have factored the denominator d tilde of x, so we've got its simple roots, its multiple roots, its simple real roots, its multiple real roots, and its complex roots. I haven't done its multiple complex roots. You could imagine if it has case 4, if these are multiple roots. If they're multiple roots, then I would expect, just as here, just as in this case, I had powers of t multiplying the exponential. Here I would have powers of t multiplying this. I'm not going to derive that for you, but it's not that hard. Where was I going with that? Yeah. So the nice thing here is if we want to get the full time dependence, obviously, once we've done the factoring, we know how to do it. However, once we've done the factoring, we don't even have to do the full inversion if all we're interested in is our system going to blow up, or is it going to go to steady state? Often, that's a pretty important question to know the answer to. If it's going to blow up, you're not all that worried about the actual time dependence. You're calling the fire department. And you can do that just from the factors. You don't have to actually do the inversion. So, for example, if you have a bunch of roots and they all have s's less than 0, I'm safe. It's stable. So, stability. 1. It's stable if all roots are real and negative. Well, I can do better than that. If even this can be stable if alpha is negative. If alpha is negative, then eventually all the oscillations die away. So not only if all roots are negative, if all roots are real and negative, or if all roots have negative real parts. That's good enough. this is, I'm okay, I can live with this. And I can certainly live with this. The system is unstable, meaning it can blow up, unstable, if at least one root of detailed events has a positive real part. I can, if I have 100 roots and 99 of them are good, but one of them has the real part greater than 0, boom. Boom. Even one. It has to be unanimous, not just the majority. Unanimous. If you want stable, they all have to be negative. You can have another case, let's imagine another case where it's unstable. It's unstable if, let's look at this situation. What if alpha happens to be 0? If alpha is 0, then this just goes as t to the n minus 1 over n factorial. As t grows, if n is greater than 1, this goes to infinity. So if at least one root, well, if there is a multiple 0 root, so if the polynomial has root 0 more than once, in other words, if I have an s squared in the denominator, or s cubed, s to the power greater than 1 in the denominator, then this is going to give me a multiple root of 0, and as long as n is 2 or greater, then it's going to be unstable, no matter what the other roots are doing. Now, it's not going to diverge exponentially, but it'll diverge polynomially. Still divergence. What if I have a complex root with alpha is equal to 0? Well, in that case, if all the other roots are stable, then the system will oscillate with bounded oscillations. So it'll just oscillate like this. This is if all the other roots are stable. If one of the other roots is not, if I'm in either of these two cases and I have this, these cases will win. So here I have conditions for stable, for unstable, unstable, and for bounded oscillations. See if I left out any cases. I think I got it. Okay. Let's just give these things names. This is a name. This is called overbear. Let me just, I never like these names because I always forget which one's which. Yeah, this is called overbear. And this one is called underdam. Did I get that right? Or did I? Underdammed. Negative. No, okay. No, I'm sorry, the other way around. This is not damped at all. This is called overdamped, and this one is called underdamped. Under is when it's complex. Did I get that right? No. This is called under and the other one's over. Sorry, under and over. So I don't like it. It doesn't really mean much to me, those names. Those are just standard terminology. Under is when it's complex. Yes. Are there any questions on that? Okay, well, let's just go back to an example. Remember we had an example of two CSTRs in series. And then we had the solution, CA2 tilde of S is equal to, and this is equal volumes, or separate, different volumes, unequal volumes. So I had 1 plus ST1, 1 plus ST2, and here I had KT. So I had the steady state, and then I had a C8 in prime zone. And this was a situation where C8 in, and this is T is equal to T, and T is equal to 0. So we had CA2 prime tilde was equal to a steady state gain times CA in prime tilde times 1 over ST1, 1 over ST2. Just make sure I got that example correct. And then there was a 1 over S. 1 over S. So let's, yes? Can you pull them out? This is KP, the steady state gain. Sure. Okay, so let's notice the denominator is already factored. So this is a numerator. The numerator is n tilde. Now n tilde of s. I need CA in prime tilde. CA in prime tilde could be a function of s. Well, actually, let's be careful. This is delta CA in. Why is that? Because CA in prime tilde was delta CA in divided by s because this was a step change. So this divided by this was CA in prime tilde. That's why I have a 1 over s here. So let's notice, so this we derived previously, where T1 or T2 was tau 1 or 2 over 1 plus A tau 1 or 2. So I have a first order reaction, A goes to product. See, someone cleaned the board, otherwise that would have still been up there from last time. It's nice when they clean the board once in a while. Okay, so this is recall. So let's notice the denominator is already factored. So here's d tilde of s. And notice that n tilde is not even a function of s. It happens to be a constant. But here it's a constant. D tilde of s is already factored. And I know what my factors are. I know that the factors, the zeros of d tilde of s are minus 1 over t1. I set this factor equal to 0. I get s is minus 1 over t1, minus 1 over t2, and s is equal to 0. So notice, what are my factors? I've got a negative, both real, and 0. Well, I'm not quite here. I have 1, 0. So it's almost stable. The only thing is, and I should have this, all roots negative. But except 1 that's 0. there. If one of the roots is 0, and there's only one of them, then I have e to the 0. What's e to the 0? 1. So that means I'll have a constant. Just a constant. So solution goes to a constant. So here, the solution goes to a constant. And what constant is it going to? Let's see. Let's look at so this tells me solution goes to a constant. And let's see what that constant is. To see what that constant is, we can use the final value theorem. The final value theorem tells me that the limit as t goes to infinity of f of t is equal to the limit as s goes to 0 plus s f tilde of s. Well, this is f tilde of s. I multiply by s. I take the limit as s goes to 0. That becomes a 1, that becomes a 1. And therefore, CA2 prime tilde of, CA2 prime of t, the limit as t goes to infinity of that, is equal to just Kp times delta CA. Yes, it goes to a constant. That's the constant. By the way, let's notice what would have happened if instead of a step function, I have CA in is a pulse. This is t. So it's a Dirac delta. Instead of this. Well, in that case, CA in prime tilde, instead of being this, is just equal to a constant. The Dirac delta times something. So it's A times 1. Where A is the integral, remember, what does Dirac mean, delta mean? It means I take a bucket of something and I dump it in. So A is the volume of the bucket. Well, it's not the volume, it's the amount in the bucket. It's the amount in the bucket. In the bucket. Well, in that case, CA2 prime tilde is equal to Kp A. Maybe I should use A because I used A over there. Let's call it, I don't know, D. A is the species, A. So D is the amount of A in the bucket. It's KPD over 1 plus ST1, 1 plus ST2. And notice the roots now, zeros, now are minus 1 over T1 and minus 1 over T2. There is no 0 root. So this is stable. And what does stable mean? Well, that means, as we'll see, let's look at the long time solution. So if we look at the final value theorem, we have the limit as t goes to infinity of CA2 prime of t. Well, I multiply by s, and I take the limit as s goes to 0. I get 1 in the denominator, and I get 0 in the numerator. 0. And what does that mean? That means the output eventually forgets that I dumped in a bucket and goes back to what it was. The output goes back to where it was. It forgets that I dumped a bucket. Are there any questions on that? Questions? Yeah. How did I get minus 1 over T1? How did I get this? Okay, I want the roots of the denominator. So the roots, a little aside. I take 1 plus st1 equals 0. It's the same thing for 1 plus st2. So st1 is equal to minus 1, and s is equal, so this is at the root, is minus 1 over t1. And similarly for minus 1 over t2. A root means the value of s that makes this thing 0. So that's s star that makes that thing 0. Other questions? Okay, again, you don't have to copy everything down now. We're going to have pictures of it. I want you to follow it and try to understand. So if there's something you don't understand, you can ask right away. Okay? Okay. Questions? All right. So these are the tools we need from Laplace transform. And notice, often the question we're trying to ask is about stability. So the nice thing is, we can answer that just by looking at the roots. We don't even have to write out the inverse. We can write it out, but we can just get the answer of stability from these guidelines and just looking at the roots. Okay, now notice when we have a physical problem, we always have a bunch of inputs and a bunch of outputs. And sometimes there are, as we said, there are going to be outputs that we call the controlled variables, the ones that we want to control. And there'll be lots of, maybe lots of inputs. Wouldn't it be nice if we could just get the one output we're interested in terms of the inputs, without all the other outputs? So for example, here I have 2 CSTRs in series. What I'm really interested in is what comes out of the second CSTR. I'm only interested in what comes out of the first CSTR, in that it influences what comes out of the second CSTR. But what I'd really like to know is what comes out of the second CSTR as a function of what comes in to the system. If I have 5 CSTRs in series, I'm really most interested in what comes out of the 5th CSTR as a function of what goes into the first. And it's nice if I don't have to worry about a cumbersome equation that has CA4, CA3, CA2, CA1 in there. And I want you to notice that when things are linear, I'm able to write CA2 prime in terms of delta CA in without CA1 prime. If you recall, when we looked at a second order reaction and we linearized it, T had the CA, had the steady state value of the CA in it. So when I had, notice here, the time constants don't have concentrations in it. It just has tau, which depends on the reactor, and K, which is the reaction. But when I had a higher order, a nonlinear system that I linearized, T had the concentration in it, the concentration about which I was doing the steady state. So then, I can't get away from having all the intermediate variables because they'd be buried in the T's, and I have a bunch of these T's. The nice thing about linear systems, if they're really linear, is I don't. I can eliminate all the intermediate variables. So that's kind of one thing we like about linear systems, that we can eliminate the intermediate variables. And we'll see that we can write output as a function of input. And we'll be able to do that with something called block diagrams, which we're going to talk about next class. We're not going to get to it this class, because I only have like 10, 15 minutes left. So there are going to be, actually, the quantity that we work with, and you see this border is too much glare. I'm not getting an answer. You don't see glare? Okay. So we're going to define something called the transfer function. G tilde of S. Where this is defined as the output, an output variable divided by an input variable when the initial condition is 0. So it's one output variable divided by one input variable with the initial condition 0. And often I have to tell you what variables it is, so it's the out. So I have some subscripts that tell me the output and the input. And that's called the transfer function. Now it's easy to have initial condition 0 when I work with prime variables, because by definition they have initial condition 0. So in this case, for example, if I wanted to have the output be CA2 and the input be delta CA in, tilde, so for CA in prime to CA2 prime, that thing is just this guy divided by this guy. So it's KP divided by 1 plus ST1, 1 plus ST2. For the two CSTRs and symbols. Notice I don't have the S here because this thing together is CA in prime tilde. And notice what it does. What it does is it pulls out anything that anything having to do with the input. So whether it's this or this, the difference is in the input. G tilde doesn't change. G tilde is the same because G tilde characterizes the system, not the disturbance. So this characterizes the system. Typically, it's the inputs that are the disturbance, are the inputs. So G tilde, the transfer function, characterizes the system, not the disturbances. And once I have G tilde, I can take any input, and see what happens to the output. So the output is just G tilde times the input. And I can just swap out the inputs. Yep.
Can you clarify the initial condition of 0 applies to the input only, or?
No, both.
Okay.
Remember, they're prime variables. So by definition of a prime variable, the initial condition is 0 for all of them. Okay, so are we all here? So can you give a picture of this board? Because I want to do a problem. A goes to problem, where at t is equal to 0, I have a step change in CA in and in V. So I have two changes going on at once. So let's write out the equations. I've got dCA dt. Here's CA, here's CA in. Is equal to the input. So this is V over big V times CA in minus CA minus KCA. So that's the standard form there. And let's notice what's gonna change now. What's gonna change is I'm gonna change this guy and this guy. And as a result, this guy is going to change. So let's notice that this term looks kind of linear, this term looks kind of linear, but this term is nonlinear because I've got this times this, and I've got this times this. So I've got to linearize all those terms. So let's notice, let's linearize V times CA in minus CA. So that's nonlinear, and let's linearize. Well, again, CA in is undergoing a step change, and V is undergoing a step change at t is equal to 0. So I've got V at t less than 0. I'm not going to write the t. This means t less than 0 over V times CA in less than 0 minus CA less than 0 plus the derivative of this thing with respect to V times this. Well, the derivative with respect to V is just that. So that's just CA in less than 0 minus CA less than 0 times V prime plus the derivative of this thing with respect to this factor, which just drops out. So that's just V less than 0 times CA in minus CA. Where if it doesn't have a parenthesis in front of it, it's for t greater than 0. And then, of course, I could have nonlinear terms. So there's a prime there. Plus the nonlinear terms. Notice what happens here. Sometimes, aside, if I have f times g, and I want to linearize it, so what I could notice is that this just looks like f0 g0 plus ddf. ddf just gives me g. That's g0 times f prime plus ddg, which just gives me f times g prime plus nonlinear. So if I don't have any complicated functions, I just have f and g, then I can just notice that the answer always just looks like this. Okay, so now I can put it all together. So I have dCA dt is equal to, and let's bring the kCA to the other side. So that's equal to 1 over V times all these guys. So it's equal to V less than 0 times CA in less than 0 minus CA less than 0 plus CA in less than 0 minus CA less than 0 V prime plus V0, V less than 0 times, I'll have to write it down here, CA in prime minus CA. Is that clear? I just plug in these three terms for this term. In other words, I've kept everything the same. And let's look at the steady state for t less than 0. That's dCA less than 0 dt to 0 plus kCA less than 0 is equal to 1 over V, V less than 0 times CA in less than 0 minus CA less than 0. And I'm going to go through the steps here now. I'm just going to subtract. And if I subtract, I notice that this and the 1 over V multiplies everything. This term cancels this term. And I have dCA prime dt plus kCA prime. So this, I have CA minus its initial condition. Here I have CA minus initial condition. And notice here, I'm going to take the V times the CA prime and move it to the other side. So here I have V less than 0 over big V, CA prime. And let's see what's left on the other side. On the other side of the equation, I've got CA in less than 0 minus CA less than 0 times V prime plus, That's this, plus the other term, v less than 0 over v, and I left out the 1 over v, times CA in prime. And this is what I'm going to want to take the Laplace transform of. Okay, so far the steps are exactly what you did on the first exam. I want you to notice that the left-hand side of the equation is the system, no disturbances. System without disturbances. The right-hand side are the disturbances. CA prime, in prime, and V prime. Everything's separated out. When I take the Laplace transform, I get S CA prime tilde plus this thing I can call 1 over tau 0 because it's V for tau less than 0. So here I just get plus CA prime tilde times 1 over T 0, where T0 is tau 0 over 1 plus T tau 0. And that's equal to this whole thing, CA in less than 0 minus CA less than 0 over V times V prime tilde plus V less than 0 over V times CA in prime tilde. Well, notice I'm trying to get to a point here. This whole thing I can rewrite as 1 plus ST0 over T0. So I can notice I can write CA prime tilde is T0 over 1 plus ST0, because this was 1 plus ST0 over T0, times this thing, CA in less than 0 minus CA less than 0 over V, V prime tilde, plus V less than 0 over V, CA in prime tilde. And this is what I wanted to get to today. Notice, here I have the denominator, and I may have contributions to the denominator from V prime tilde and C and A in prime tilde. Because these are step functions, I could have 1 over S's coming in from them. However, the rest of the denominator, D tilde, comes from the system, comes from the left side of the equation. So this comes from the bulk of the denominator is the system. It's independent of disturbances. So the left-hand side characterizes the system. The denominator characterizes the system, not the disturbances. And that's the point I want to make here, is the denominator comes from the left side of the equation, which is the system. See if there's anything else I want to say about that. Obviously not going to have time. Well, actually, I don't even have to solve it. I just want to give you the G's. The, what did I call it? The transfer functions. Notice, this thing times this is the transfer function of CA prime tilde over V prime tilde. Did you take a picture of this board already, or not? You did. Good. So I can just write out the transfer functions, which is all I wanted to do for this problem. So I have G tilde of CA prime tilde V prime tilde is equal to CA in less than 0 minus CA less than 0 times V, divided by V times T0 over 1 plus ST. And G tilde of CA tilde CA in prime tilde is just equal to V at t less than 0 divided by V times T0 over 1 plus S T0. And by the way, this is just T0. So I just get 1 over S, 1 plus S T0. In other words, here I have the response of CA prime to changes in the volumetric flow rate and to CA in prime tilde. If only one of them changes, well, that term drops out. Notice, because the system is linear, because I've linearized the system, the responses of CA in prime tilde add. They add because I've linearized. Had I not linearized, they wouldn't add. Then they would have been multiplied by each other. But they add here. And we can write these transfer functions, which again gives me the output in terms of the change in the output due to the change in the input. Change in the output due to the change in the input. And here we can see it from this particular problem. Are there any questions? I think we're done for today. Questions? I hopefully will have your exams. I'm going to be grading them tonight, so hopefully I'll have them for you next time.